Alkali aggregate reaction, or AAR, is a chemical reaction that occurs in concrete between the alkalis, like sodium and potassium, in cement, and certain types of aggregates. This reaction produces a gel-like substance that expands in the presence of moisture. This expansion creates internal pressure within the concrete, leading to cracking and deterioration. AAR is a significant concern for concrete structures, impacting their durability and longevity. There are two main types of AAR: alkali silica reaction, or ASR, and alkali carbonate reaction, or ACR. ASR is the most common type and occurs when the alkalis react with silica found in aggregates such as chert, flint, and some sandstones. ACR, on the other hand, involves the reaction of alkalis with carbonate rocks like dolomite and limestone. Both ASR and ACR can have detrimental effects on concrete structures. The reaction between alkalis and aggregates is a slow process that can take years or even decades to manifest. Factors that influence the rate of AAR include the alkali content of the cement, the type and reactivity of the aggregates, the moisture content of the concrete, and the temperature. Understanding the mechanisms of AAR is crucial for developing effective mitigation strategies and ensuring the long-term performance of concrete structures. AAR can significantly impact the structural integrity of concrete. The expansion caused by the reaction products generates internal stresses within the concrete, leading to a reduction in its mechanical properties. One of the most notable effects is the decrease in compressive strength, which is the concrete's ability to resist being crushed. This reduction in strength can compromise the load-carrying capacity of structural elements. In addition to compressive strength, AAR also affects the tensile and flexural strength of concrete. Tensile strength refers to the concrete's ability to resist being pulled apart, while flexural strength measures its resistance to bending. The formation of microcracks due to AAR weakens the concrete matrix, making it more susceptible to failure under tensile and flexural loads. This can lead to cracking, deflection, and even collapse of structural members. Furthermore, AAR can also impact the elastic modulus of concrete, which is a measure of its stiffness. The expansion caused by the reaction products disrupts the internal structure of the concrete, reducing its ability to return to its original shape after being subjected to stress. This reduction in stiffness can result in increased deflections and vibrations, compromising the serviceability of the structure. The consequences of AAR can be severe, leading to significant damage and costly repairs. One of the most visible signs of AAR is the formation of map cracking on the surface of concrete. These cracks typically appear as a network of interconnected lines and can vary in width and depth depending on the severity of the reaction. The formation of cracks not only affects the aesthetics of the structure, but also compromises its durability. Cracks provide pathways for water and other harmful substances to penetrate the concrete, leading to accelerated deterioration. Water ingress can cause corrosion of steel reinforcement, freeze-thaw damage, and chemical attack, further weakening the structure. Moreover, the expansion caused by AAR can also lead to increased permeability of the concrete. Permeability refers to the ability of fluids to flow through a material. As the concrete expands, it creates interconnected voids and microcracks, increasing its permeability. This allows for easier ingress of water and other aggressive agents, accelerating the deterioration process. Addressing AAR requires a comprehensive approach that involves both assessment and remediation techniques. Assessment methods aim to determine the presence and extent of AAR in existing structures. One common method is petrographic analysis, which involves examining concrete samples under a microscope to identify the characteristic reaction products. Once the presence and severity of AAR have been determined, appropriate remediation measures can be implemented. These measures can range from simple maintenance practices to more complex structural repairs. One common approach is to control the moisture content of the concrete, as moisture is essential for the AAR to progress. This can be achieved through surface treatment such as waterproofing membranes or by improving drainage systems. In more severe cases, structural repairs may be necessary to restore the integrity of the affected elements. This may involve removing and replacing damaged concrete, injecting cracks with epoxy resins, or strengthening the structure using external reinforcement.